Welcome to this specialized mathematics lecture on triangles, designed for Class 10 students. Among all geometric polygons, the triangle holds a place of supreme architectural and mathematical importance. In engineering, triangles are the fundamental units of structural rigidity. Unlike rectangles, a triangle cannot be deformed without changing the length of its sides, making it the silent hero behind bridge trusses, radio towers, and structural roof frames. Today, we step into the mathematics of triangles to master the deep concepts of similarity, proportional lengths, and geometric scaling. In this course, we will move beyond basic shapes to prove rigorous geometric theorems, unlocking the mathematical keys that allow architects, space engineers, and computer graphics designers to model our physical world with absolute, unyielding precision. Let us establish the core logical distinction between congruence and similarity, which represents a crucial step in advanced geometry. In earlier classes, you studied congruent figures, which are identical in every single way. They possess the exact same shape and the exact same size. If you place one congruent figure over another, they cover each other perfectly. In contrast, similar figures are those that have the exact same shape, but not necessarily the exact same size. Think of similarity as looking at a photograph of a building. The photo preserves all the angles and proportional shapes perfectly, but at a scaled-down size. Geometrically, two polygons are similar if and only if their corresponding angles are perfectly equal, and all their corresponding sides share the exact same scale ratio. Tracing the comparison dashboard, observe how identical congruent shapes compare directly to proportional, scaled similar shapes. We now introduce one of the most famous and foundational theorems in all of mathematics, the Basic Proportionality Theorem, also known as Thales' theorem, named after the ancient Greek philosopher Thales. The theorem states, if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, then the other two sides are divided in the exact same ratio. This is a beautiful and surprising geometric property. It means that drawing a simple parallel line creates an invariant relationship, a ratio that remains constant regardless of the size or angles of the triangle. Tracing the triangle on your screen, notice how the parallel line DE intersects sides AB and AC. BPT states that the ratio of AD to DB is exactly equal to the ratio of AE to EC. This theorem is the foundation of geometric scaling and triangle division. Let us walk through the elegant step-by-step mathematical proof of the Basic Proportionality Theorem, which is a required proof for Class 10 students. The strategy is based on comparing the areas of triangles sharing the same altitude. First, we construct helper lines by joining B, E, and CD, and draw altitudes EN perpendicular to AB and DM perpendicular to AC. Now, let us calculate areas. The area of triangle ADE is half base AD times height EN. The area of triangle BDE is half base BD times the same height EN. Dividing these areas simplifies directly to the side ratio AD over BD. Similarly, using the other height DM, the area ratio of ADE to CDE simplifies to AE over CE. Finally, notice that triangles BDE and CDE are on the same base DE and between the exact same parallel lines DE and BC. Therefore, their areas must be equal. This forces our ratios to be equal, completing the proof. In mathematics, proving a theorem is only half the journey. We must also analyze its logical opposite, which is the converse. The converse of the Basic Proportionality Theorem states, if a line divides any two sides of a triangle in the same ratio, then the line must be parallel to the third side. This means that proportionality forces parallelism. We prove this converse using the method of contradiction. If we assume the dividing line DE is not parallel to BC, we can draw a hypothetical parallel line DE prime. Applying BPT to this parallel line yields a ratio that conflicts with our initial given proportion. This mathematical contradiction proves that E prime must coincide with E, meaning the original dividing line DE must be perfectly parallel to BC. Tracing the visual grid, see how proportional cuts mathematically restrict the line's angle, forcing a parallel state. To solve complex geometric shapes, we do not need to measure every single side and angle. We use specialized similarity criteria. The first is the angle-angle-angle, or simply AAA, similarity criterion. It states that if in two triangles, the corresponding angles are equal, then their corresponding sides are proportional, and therefore the two triangles are similar. In fact, because the sum of angles in a triangle is always 180 degrees, if we know that just two angles are equal, the third angle is automatically equal. Thus, we can simplify this to the AA similarity criterion. Observing the first panel on your screen, see how matching angles guarantee that the triangles are scaled versions of each other. This AA rule is incredibly powerful, allowing surveyors and engineers to establish similar systems using only basic angle measurements. The second key rule is the side-side-side, or SSS, similarity criterion. It states, if the corresponding sides of two triangles are proportional, then their corresponding angles are automatically equal, and therefore the two triangles are similar. This is the logical converse of the AAA rule. It means that if you construct two triangles where all side lengths are scaled by the exact same multiplier, such as a 3-4-5 triangle and a 6-8-10 triangle, they are mathematically guaranteed to have the exact same interior angles, forcing them to be similar. Tracing the second panel, observe how the proportional side ratios of 3/6, 4/8, and 5/10 all simplify to 1/2. SSS ensures that scaling structural lengths perfectly preserves the interior angles and overall balance, which is vital for building stable scale models. The final major criterion is the side-angle side, or SAS, similarity rule. It states, if one angle of a triangle is equal to one angle of another triangle, and the sides including these angles are proportional, then the two triangles are similar. It is critical to note that the equal angle must be the included angle, the one nestled directly between the two proportional sides. If the angle is placed elsewhere, similarity is not guaranteed. Tracing the third panel, notice how the highlighted angle is surrounded by sides that scale in ratio. For example, a side of 4 scales to 8 and a side of 6 scales to 12, enclosing a matching 60-degree angle. By locking down just two sides and their included angle, SAS gives designers and programmers the exact mathematical coordinates needed to duplicate and scale similar elements in computer graphics. How do we measure the height of an enormous structure, like a light pole, a pyramid, or a tall building, without climbing it? We use the elegant science of similar triangles. This technique, called indirect measurement, was first used by Thales to calculate the height of the Great Pyramid of Giza. Imagine a vertical light pole casting a shadow on the ground. At the exact same time, a student of height 1.8 meters stands nearby, casting a shadow of 3 meters. Because the sun's light rays hit the earth at the same angle, they form two similar right-angled triangles. Using our similarity proportions, the ratio of the pole's height h to the student's height is equal to the ratio of their shadows, which is 7/3. Solving this simple equation gives the pole's height. H equals 1.8 times 7/3, which simplifies to exactly 4.2 meters. This method drives modern radar, navigation, and satellite distance scaling. Today, we have completed a profound geometric journey through the study of triangles. We learned to differentiate between congruent and similar shapes, proving how similarity preserves shape via proportional side scaling. We proved Thales's famous basic proportionality theorem, demonstrating that parallel lines split sides in equal ratios, and analyzed its parallel forcing converse. Finally, we mastered the AAA, SSS, and SAS similarity criteria and applied them to calculate heights indirectly using real-world shadow scaling. Tracing the triangle's summary mandala, observe how theorems, side ratios, scaling criteria, and physical light rays align in perfect geometric beauty. These triangle relationships are the silent math structuring our modern world, running behind structural engineering, 3D computer rendering pipelines, geographical surveying, and the GPS systems mapping our physical universe.